Hello. Well, um, today we'll be talking about kind of riding the same wavelength as Casper's presentation. What is the most important feature that you want to have gotten right when you're designing an agentic system or an AI agent? And that is context or knowledge. So we'll be talking about a little bit of how the most popular way of doing RAG is a little outdated for today's standards, how to adapt it to the agentic era, and show a little bit of a case study that we did and run some experiments and hopefully spark some inspiration in you guys. My name is Mario. I'm a nexos.ai engineer.
And I'm Povilas, the technical lead.
Yeah. So retrieval augmented generation. It's become quite popular at this point. You probably all heard of it. It's probably the simplest way that you can get context into your agent. But it's not entirely obvious when you should use it. So let's take a step back and think about, do you even need RAG in the first place? When is it useful and when is it not? Because it's this very shiny tool that everyone's very excited about, but it's not always the best fit solution. So there's this chart that I really like. It basically shows you that the more dynamic your data is and the more domain expertise you need, the more you need to transition towards more transient methods. So there's this definition that we call parametric learning, which is the types of training that you will see on the top of the graph, such as training your model, reinforcement learning, or fine-tuning. Also updating only like the last layers of the transformer, for example. And then if you're working with data that will change more often, that you don't want the model to memorize forever, let's say you have many users, like the name of each individual user, you don't want that to be memorized and taking up space in your agent. So that will be the transition more towards more transient methods of learning or context injection, such as retrieval augmented generation or in-context learning, which is just another way of saying some sort of prompt engineering. And so this is important for us to understand why the current implementations of RAG are a little bit outdated. So originally when RAG came out in 2020, or even before that, before transformers used it, it specialized in a specific type of problems called needle in a haystack. And at the same time, it's also the problem that it's hard for it to solve. The way it solves it, it requires certain assumptions, such as having a very clean and organized data, but that is often not the case for real-world data. So if in the perfect scenario, you will have a query, the user will say something, and then you will compare that to your embedded documents using some sort of distance metric like cosine similarity to see if the query and the document are similar, and then you will take the most similar result, give that to an LLM, and then find the result. However, what happens if you have a lot of junk inside your data? Like you have a bunch of chunks that just are completely unrelated to the specific questions that you have. What if you have 2 or 3 or more documents that are actually pretty similar to what you're looking for, but not quite yet? For example, if you want to look for financial report of 2025, there is a very high likelihood that it could return the financial report from previous years or some financially related terms and not exactly the data you want. And then how do you ensure that that's not going to happen? And also, lastly, like what if the structure is not there yet to support it? So this kind of brings us into a very important point of we need this structure for RAG to work. Otherwise, it will just be chaotic. And the reality is that more often than not, your data will be unorganized, unsanitized, and completely all over the place. So the question is, how can we turn this chaotic data into something organized, but at the same time without wasting a bunch of manual effort and a bunch of human in the loop and domain-specific knowledge, and turn it into something that's LLM processable and human readable? And this is the field of knowledge organization. And there's a lot of principles before we dive into our case study, but just so you guys have in mind, there's a bunch of things you can do here, and you can explore in your own time, but we list out kind of the most influential ones. that will probably affect the majority of the performance that you will want to see. The first one is chunking. So you have to think about how you want to segment your data. It's not the same to just cut it into fixed sized pieces or document that you have, or have some sort of semantics relationship or boundaries in order to receive more chunks that make sense. The second one is some sort of clustering and categorization. So if you think about it, if you're using a simple dense passage retrieval using an embedding model, it will be naturally kind of segmented throughout the embedding space, and then you will have some sort of natural semantic meaning. But there's other ways that you can improve that. Then you could also dive into some sort of feature extraction. So for example, for your documents, you can divide them by what kind of documents they are, maybe also add certain labels such as dates or values or prices or investment returns, whatever. And you could also even model certain relationship between them. And for this last point, we will be diving a little bit into graph RAG or knowledge graph domain space, which is also a very actively and interesting area of study. So the bottom line is, if you want high quality retrieval, it starts with structure. You cannot feed it chaos into an LLM and expect good results.
So we were trying to kind of understand how we can make it a bit simpler and running a couple of experiments. And here I'm going to present one of a case study and experiment that we kind of did, and we call it the context-aware knowledge tree. So how does this work and why we are trying to do this? So at nexos.ai, the primary focus is working with enterprises, and that means that we have a couple of challenges that we face every day. So first of all, we are working with abundant amount of knowledge, the knowledge that is spread through various domains, so from legal to marketing to development. That means that any system that we build must be efficient and able to work with it rather fast, because we just have to support a large amount of information. The other important caveat, as typically for the enterprise, where knowledge and where information is the most prized possession, we need to take a lot of steps making sure that we do not leak this information to any third parties. You don't want that this information would be known to your adversarial people, that people would know your architecture, that people would know your financial reports. So that kind of boils down to that we always need to use self-hosted models where you can trust where all the data always exists. It cannot be used by to a simple third party if you do not have a proper legal agreement with it. So you kind of want to know everything. And finally, the information is always dynamic. Every day we create thousands of new documents, we create thousands of new content, and if we cannot process in one day what we create in one day, and then your system will just break. So to do this, we kind of need to go through three main steps, and then we can talk about the results that we saw from this approach. And those steps are chunking, clustering, and retrieval, as that probably sounds like for any proper RAG implementation. First aspect that we need to delve a bit more in depth to, as Mario kind of explains, there's like very simple, trivial ways we can do chunking. We could try to fit the entire documents, that would probably wouldn't fit into the context. We can do the sliding window, this is a general approach, but we will likely cut off at unimportant areas. So we would, and ideally, for what you will see a bit later, we actually want to find out concrete facts or statements in the documents, not just an arbitrary factual data added somewhere. And we don't want combinations of those data. So there are like more interesting chunking techniques. So one is called semantic chunking, where you use the embedding model itself by first creating the chunks, then, first creating the chunks, then running it through the embedder and getting the, basically finding which chunks are actually aligned together and which ones are separate. So using the embedding the model's knowledge itself to chunk it. The other one is using some specialized chunkers. So if we imagine that we have Lithuanian in English language, you would need a different grammar rules to split the data. And you would also need different grammar rules to split any code or any other like grammatical areas. This would be a bit more labor intensive on the developer side because you need a way to identify the document, you need a way to add and expand new grammars, and if something gets updated, you need to constantly monitor and add it. And then there is more inference and computational intense ways, like using LLM-based chunkings, which typically performs quite well, but this means that you are potentially introducing hallucinated knowledge into your chunk data, and you're also requiring to use a lot of inference at the chunking time. Finally, we kind of found that one technique seems the most promising out of them, and that is something called lane chunking. So if you ever have looked into the model itself and saw what's happening, you would find that you actually don't need to go and embed one thing at a time. You can put everything that fits into the model context, and you wouldn't get just the last embedding vector for the entire domain. You have it for the entire token. So what you can do for the semantic chunking, you can actually do per token level with the same computational power you need for a regular embedding. And this kind of has a nice property that not only you split at the model's semantic important areas, but you also have an embedding vector which represents the entire document, not just a small piece that you embedded. So why am I talking about chunking so much? Because then we have chunks and we have vectors, we have something interesting we can do. We can start trying to clusterizing and trying to automatically understand what's in the data. So for example, here we took our API service, we clusterized it, we embedded and chunked it and then clusterized it. And what we see that we naturally, by using a simple k-means algorithm, detect categories in our code base. This means that, for example, that smaller blob is our data structures, some in-between areas, like sharing some computational or logical paths in our code base. And the other thing that we can do, which almost gives us a kind of a graph, a tree, if we have a very large data set and our clusters are big, then you can cluster those clusters again and build a tree structure which automatically gives you a structure for exploration of your data and your corpus. This is interesting because this allows us to do a bit more intelligent retrieval techniques, which are basically not only you're looking in the needle of a haystack, you're actually finding for which specific category in your data it belongs to, and then you can tie it to that hypersphere in the semantic space. Hopefully getting more concrete answers. And as Mario was using an example of, you are looking for something from 2015, which is your financial report. Well, technically, maybe you will find that all of them are clustered in a similar location in your semantic space, if you embedded them properly. The other interesting thing that you can do is that you can kind of solve the ability for the model to get the general knowledge about the system. Instead of just going and using the final leaves, you can take those clusters, sample a bit of points, and determine what is the theme of that point, building this summary and knowledge tree for your data set, and adding that into the graph, into your generation process, basically gives you something that you would only achieve by properly fine-tuning or properly managing your documentation. So it's an automated way to remove both duplicates and give you a general information about the system. So this entire experimentation, we tried to run performances against natural RAG, and we kind of got around 9% improvement for the system. There's a similar results if you're using simpler techniques like clustering by BM25, which could be a possible direction to even make it this a bit cheaper. And of course, it has a capability which never properly existed before of answering the general questions or having the overall structure of a project. There is some limitations though. There's the improvement accuracy we would prefer to be better, but maybe there's some missing in our experimentation. There's always more to do. We haven't fully capitalized on the graph structure, but for that we have we are coming to an agentic era, and we are are potentially able to do something a bit more interesting.
Yeah, so speaking of that, so we are very interested in continuing like to explore this. So some of the things that we can try that we were thinking just on top of our heads was like to try with even more structure. And this was, let's say you know that you will be working with specific financial data, then you can already predefine certain like a set of ontology or a relationship between your data points, and also have them also completely automatically generated. Then also, as Povilas mentioned, there's other methods besides semantic similarity. You can use BM25 or like sentence-wide similarity, like with SBERT. And then also trying different chunking strategies, such as using grammar-based chunking by, like, let's say if your code, you want to embed this code base, and none of the chunking strategies work well for you, then maybe you can try a grammar-based one that divides each function and each object into a classification, and hopefully providing better results. And yeah, so lastly, we wanted to show you guys two kind of practical and bonus applications that came out of this structure experiment to kind of show what we can build upon once you have an organized knowledge base, and how we can expand your work into the future. So the first one we call agentic knowledge transversal. This I particularly like because it reminds me of those traditional artificial intelligence problem-solving algorithms or like optimization problems. The idea is let's say a user has a query, like give me financial report 2025, gives that to the agent, and then the agent will have a set list of actions that they can do. So in this example, we give it 3. The first one is go up. So let's say, given the query, it will land somewhere in the graph that we were saying. It's kind of in a tree structure. And it lands in a specific node based on semantic similarity. Then it can either go up and go to the parent node, go down to one of the children nodes, or expand or explore the current node and see all the leaves in the current node, and aggregate that knowledge in order to inform its next action. And as you can see, this is an iterative loop that lets the model also update a scratchpad and iteratively transverse this knowledge graph, the knowledge graph that used to be completely chaotic and unstructured, and hopefully find a good answer. So let's say even in the worst case scenario, you look for financial report 2025 and you land in the financial report 2024, the model will be able to, let's say, go up a node and see the general financial report nodes, then explore it and see, oh, I see a children node that talks about financial report 2025, and then go down that node and give you the inaccurate answer. So this essentially creates and leverages the best things of both worlds, having all the benefits of graph RAG and agentic flow, and at the same time not having the manual and tedious process of organizing and labeling each data point you have and finding relationship between them. And then the second and simpler even solution we call guided knowledge transversal. And you can imagine, instead of letting the agent do that, you kind of prompt a user to explore this semantic space. So as we said, we have this tree that was already constructed, and our user sends a query, for example, explain our architecture or code base. Depending on where this lands, we can let our system expand the closest nodes using some sort of algorithm to sample the closest chunks towards where it landed already. And this, we can cluster them into different directions. And for each cluster, we kind of reverse engineer a question to ask the user again so that they can continue exploring the space using the type of questions we give them. Like, for example, let's say 2 of the closest nodes are the backend and then the front-end codes. Then we can generate a question for each and then prompt the user, and then the user will be able to explore their own knowledge graph without having to know anything about the project, without having to organize it. They'll be able to know what's going on. And one of the particular things that I wanted to emphasize, like after talking all about this, is, and it's funny enough because this little image we included this morning, we saw like 2 more of them in LinkedIn. Like every day people are saying RAG is dead, RAG is dead because of this other thing, but this kind of ties back to the first graph we showed, this little pyramid, inverted pyramid. Graph is not dead. You can't kill something, like you can't kill prompt engineering. It's just one of the methods you can inject context into your system. The only way you can do is maybe you can mess up and not do it correctly because maybe it's outdated, it's just too naive, but that doesn't mean that the method itself doesn't work. So if there's one key takeaway for you guys, it's that knowledge organization is key. If you want your agentic tool or agentic workflow to work, you need to have organized knowledge and you need to have the right context to feed into it. So make the most out of your systems to empower your agents. Thank you so much. Yeah.
Thank you very, very much, guys, for a great presentation. And just like last time, please do raise your hand if you have a question. We have one over there.
You can take
it. Can you hear me? Okay, so as far as I understand, you described kind of graph rack, am I right?
Not really. That proper graph rag, you would use like a graph database, and it would use this LLM-based extraction to find entities and then find relationships between processes. Like you can say that a tree is like a subset of a graph. So in that sense, it's just like automatically generated using the vector space, not some kind of exploration process to define entities.
From one side, I agree with you, but look, you created a tree. It's a graph. Yes.
Yes.
It's a graph. Also, you mentioned you use it parsing, grammar-based parsing. I suppose you extracted subject, verb, object, or something like that from sentences. No.
No. So the main thing, like probably like another approach, is still to use a proper graph that has more than one relationship, which has an ability to define more relationships. It's just that typically it requires way more inference time and computational time to accomplish this properly.
It depends. And also you mentioned that you use plain chunking approach, but have you tried to use hierarchical chunking, right?
So specifically semantic recursive or like a different approach?
No, different. When you can first split document on a simple chunks, then aggregated chunks, and aggregated chunk, and eventually to the document level.
Yeah, so the one thing that we kind of encounter when we are trying to always use locally hosted models or like self-hosted models is that we need a lot
problem with document context size, right?
Yes. We are kind of like embedding time is limiting a lot of things what we would want to do, and we don't want to send it to like OpenAI or somewhere where it would be like scalable in a very trivial way, let's say.
But you can use summarization to reduce.
Yes.
Okay, but it's a technical. Sorry. Thank you.
Yeah.
Thank you for your answers.
Hello. I would like to ask, in general, how you validate the systems. Does it require any human knowledge or of domain knowledge when you create something, or do you utilize some sort of metrics to validate after?
So for this evaluation, we kind of are generating the ABCD pairs for the to make a questionnaire out of some kind of corpus, and then going through it and manually like selecting a couple of better cases and trying to get a definitive set of good enough questions, and then just running ABCD evaluation. So it's for this case, it's similar. For the Nexus itself, we kind of have this evaluation CI/CD, which has multiple metrics. Like ideally, you always have some kind of evaluation for your overall system, and then you have like ability to dig into subcomponents, because the overall point is good to notify you that something went horribly wrong, and then you go into smaller and more precise test, and every case is kind of a bit unique. To dig in where the actual problem is arising from.
Okay, I'm looking for hands. Okay, so if you don't have any more questions, thank you very much, Povilas, Mario. Yes, give it up for them.